Welcome to Chemistry Plumbum. Today we will see bond parameters. Bond parameters tells about bond length and bond strength and bond enthalpy and bond order and resonance structure and polarity of bonds. See, let's see first bond length. See, if you take one small size atom, one big size atom, see the bond length. This is the radius R. Here hydrogen has small size atom, chlorine has big size atom. See the bond length. This is the bond length. See below. Bond length defined as radius between the two atoms. Bond length measuring between the two atoms. Type 1 covalent radius. C. Equivalent sharing the electron between the two atoms. For example, diatomic molecules. We know that diatomic molecules H2, N2, O2, F2, Cl2, Br2, I2. These types of diatomic molecules occurs naturally. Next example, fluoride. We can see fluorine atom. So fluoride F2, fluorine is single fluorine atom, fluoride is 2 fluorine atom. See the radius between the two fluorine atoms. Here 2 fluorine atom has same size because both are same element. See below. Here both atoms orbitals overlapping at outermost orbitals. Both are equally sharing the element, so it is going to involving the overlapping to form bond formation. Next, if a total distance between the two atoms divided by 2, we will get the value. This is called a covalent radius. For first fluorine atom, the radius is 64 and the next one 64. So equal to F2 9.6 pm picometer. Type 2 vanderwaals radius. See the vanderwaals radius. Here totally 4 fluorine atom. This is one diatomic molecule of the fluorine atom. This is the one fluorine molecule, diatomic of the fluorine atom. So totally 4 fluorine atom. See the radius between these two molecule. Here this is not atom. So this is the one F2 molecule. This is the another F2 molecules. See the radius between them. It is the radius. See below at the center point. Here 2 molecules between the radius called vanderwaals radius. This is called vanderwaals radius. Vanderwaals is means that is a scientist. He is one of the famous scientists. So one F2, one molecule, another F2, another F2 molecule to give 2 F2 molecule, 2 fluorine diatomic molecules, totally 4 fluorine atom. If total distance between the two molecules radius divided by 2, we will get 1f2, 1f2, this value is 147 and 147 divided by 2, so we get 22.05 picometer or pm. This is called vanderwaals radius. Next, band angle. It is determined by spectroscopy instruments. Band angle depends on the electronic configuration of the atom. See the example for water. Here bond angle decided by lone pair electron. So this electron is the decide the bond angle because due to electrostatic force. So this band angle is 104.5 degree. Next, beryllium dichloride. So this shape is like bent. Next, BeCl2, beryllium dichloride. See here, both side chlorine atom, so there is no any electrostatic between them, so both are as equally force of attraction. So this molecule has like linear shape. So this molecule 180 degree. Next, BF3, boron trifluoride. See the boron trifluoride. See all are 120 degree. So here is also same thing. Here both side, all side has fluorine atom. So the same atom. So all fluorine atom sharing the electron or force between them equally. So this compound attain 120 degree between them, 120, 121. Bond enthalpy. Next, enthalpy means heat. The amount of energy required to break one mole of bonds of a particular type between in the gaseous state atoms or molecules. See below. For example, H2O gas. This is the H2O gaseous condition. So H2 is 1 mole atomization or break. If we atomization the H2 molecule, atomization means break. If we break the 1 mole of H2 gas, so this is going to split H plus H. So required energy or enthalpy is, here delta is changes. A means AH is atomization enthalpy. Please keep it in mind. AH is atomization enthalpy. So this value is 435.8 kilojoule mole power minus 1. See below. Here del is changes, A is atomization, H is enthalpy or heat or energy. Here H2 molecules break by separate two hydrogen atom. This is called atomization, or it is called atomization enthalpy or bond enthalpy. We can say like this. Next, O2, oxygen molecule. We know that oxygen makes double bond structure, so we can write below. See the 1 mole of oxygen gas, when we put at atomization or break, So it is going to O plus and O plus gas. Sorry, it is going to O single atom, another O single atom, both are gaseous condition. So here atomization energy, recovered energy 498 kilojoule divided by mole minus 1. See here bond strength is more than H2 molecules because double bond structure. We already see H2 molecules. So here bond strength is more than H2 molecules. Compare the recovered energy for H2 molecules. See again. So here we spend more energy than H2 molecules. See the values above. Next, nitrogen molecules. We know that nitrogen makes triple bond structure. See, this is 1 mole of nitrogen gas. When we put the atomization, it is going to nitrogen, single nitrogen and single nitrogen gas. So atomization energy is 94.60 kilojoule mole power minus 1. Recovered enthalpy. See, here something wrong, please wait. See, the recovered energy is, sorry, recovered energy, atomization energy is 946.0 kilojoule per mole minus 1 recovered energy, because this is the triple bond structure. Here we spend more energy than H2 and O2 because N2 is triple bond structure. So other example, HCl. So 1 mole of HCl, this is the solid, HCl solid. But at a gaseous condition, we put atomization or break the bond between the H and chlorine. It is going to H single atom and chlorine single atom. Both are gaseous condition. So recovered energy is 431.0 kilojoule mole power minus 1. See below. Note, H2O2 N2, these types of molecule is called homonuclear diatomic molecules. Next, H2O water. Here 3 atom, this is called heteronuclear diatomic molecules. See the below. Step 1 for water. Please see carefully. Water. How to atomization water molecule? Because here 3 molecule. See the steps. Step 1, H2 at gaseous condition. We put the atomization here. H2 splitting H and OH. So required energy is 502 kilojoule per mole. Next, step 2, again, so this is the first step. Again OH, this OH going to the break Again OH is going to the separate or break OH at gaseous condition, atomization. This is going to split single hydrogen and single oxygen. So see the energy. Here required energy is 427 kilojoule per mole. So see below average bond enthalpy. So average bond enthalpy for water molecule 502 plus 427 divided by 2. So we will get some amount of value, that is see below, that is 464.5 kilojoule per mole. H2O bond enthalpy is equal 464.5 kilojoule per mole. So this topic is over. Please subscribe the channel. More videos on the way we are making for all chapter at easy way. Thanking you all.